Question 13 of the practice exam. A force of 785 newtons is applied to a cart with a mass of 68 kilograms. The cart is rolling with an initial velocity of 12.9 meters per second west. The force acts over a displacement of 17.5 meters west, causing the cart to accelerate to a velocity of 24.7 meters per second west. What is the work done by the force on the cart? So let's write down some things that we've got here. We've got the force. We have the mass. We have an initial velocity. And we have a final velocity. And we have a displacement. So that's what we've been given in this question. And the question is what is the work? What is the work done by the force on the cart? Well, the cart, there's a force on the cart and it makes it accelerate from one velocity to another velocity. Therefore, there's been an increase in kinetic energy. So you can do this problem simply using this. The work equals the change in energy, and it's going faster now, so it has more kinetic energy, and the change in energy in this case is going to be the final energy minus the initial energy. And once you've got that in place and you realize that we're talking about kinetic energy, not gravitational potential energy or elastic energy, then the question is actually fairly straightforward. It's just the final kinetic energy minus the initial kinetic energy. If you want, you can factor out the mass and the half. Or you can just plug the numbers in. It doesn't make a difference. You'll get the same answer either way. Then plug in the mass, plug in the velocities, and that's going to, what was the mass? Don't forget to square the velocities. Don't forget to use brackets where you need them. And that spits out an answer of 15,000, and which is C. 1.5, 1 times 10 to the 4 joules. 14 says a crane is lifting a load of lumber with a mass of 356, and it requires 1.25 times 10 to the 3 joules of work. So the work done is 1.25 times 10 to the 3 joules to accelerate the mass to a constant upward speed of 0. Velocity final 0.45 meters per second. What is the change in gravitational potential energy during the upward acceleration? Okay, and again, this is a work theorem question. So the work theorem says, green, that the work done on an object is the change in kinetic energy plus the change in potential energy. So first thing you got to realize is that, so we're lifting an object, it's accelerating. So if it's accelerating, it has a change in kinetic energy. It says it lifts it up to a constant upward speed. So we'd have to assume that the initial speed was 0. So it's accelerating. It has a change in velocity, therefore the kinetic energy is changed. We're also lifting it up against gravity, so therefore the potential energy has changed. And they've given us how much work it takes. So they've given us this value right here, and they're asking us what is the change in gravitational potential energy. So they're asking us to solve for this variable. So we can manipulate the formula, rearrange the formula here, and then just solve for delta EP. Okay, so the work minus the change in kinetic energy, and we're going to have to assume that it starts from an initial velocity of 0. So the change in kinetic energy is simply change in kinetic energy would be the final kinetic energy, EK final, minus EK initial, and since it has no velocity when you're beginning to lift it, then the EK initial is just 0. So that's why this delta here, delta. That's why the delta, we didn't need a final minus initial because it didn't have any kinetic energy to begin with. And that will give you an answer of 1,214. Which is D. Number 15. So number 15 is one of those questions that may look complicated, but it's actually fairly easy. And they can ask you a bunch of questions regarding a problem like this. They'll give you a diagram, and they'll say, at this point here, it has so in this specific question, they're saying, at that point, at H1, the 6.2 kilogram block has, it says at the instant the block passes over the tip of H1, it has a speed, so it has some velocity. Oops, what is that? 1.771. So if it has velocity, it automatically has kinetic energy, and it's 3.96 meters above the ground. So therefore, it also has potential energy. This is probably one of the simpler questions you can ask about this. The question says, what is the mechanical energy of the block at that instant? So if it's just asking for mechanical energy, it's just the total kinetic energy, the total potential energy. And plug the numbers in. You've got the mass, you've got the velocity, you've got the height. So this is a very straightforward question. Well, what they may ask you in a question like this is they may say, okay, if H2 is, let's say, 2.4 meters, then what is the velocity at this point? So that's, and as a matter of fact, there's a question later on in this that does that, so we won't go over it right now, but that's the question they may ask you with this type of scenario. I don't know, anyway, back to the original question they asked. So plug in the numbers, and you can do that. It's not a tricky one. You get 250 joules is the answer for 15, so that will be B. 16, we've got a spring question. You've got a block, hits a spring, and it says it comes to rest, then accelerates to the left until the block returns to its original position. So basically, this block just goes like that, goes that way, and then goes back. So it's just going to oscillate, which is the last unit that we do. It's about oscillations and waves. So it's just going to oscillate. In this question, they're saying that in the above diagram, it's a 5 kilogram block, and it's traveling at 8.5 meters per second to the right. When it comes into contact with a spring that has an elastic constant of 9.6 times 10 to the 3 newtons per meter, what is the distance x when the block has come to rest? So some important things in this question are, well, that's the most important thing, when it comes to rest. So the block is traveling along here with kinetic energy. It hits the spring. When it starts compressing the spring, it is gaining elastic potential energy, and then it comes to rest. So in other words, all of the kinetic energy is converted into elastic potential energy in this specific question. And the question is asking for what is the distance. So this is a mechanical energy question. And you can simply say that EM equals EM prime. If you want to go through all the steps, it would be EK plus EP equals EK prime plus EP prime. But we know before it had no elastic potential energy, so this one becomes 0. And then when it comes to rest, it has no kinetic energy, so this becomes 0. So really what you're left with is EK equals EP prime. And the formula for EK is 1/2 mv squared. The formula for EP is 1/2 kx squared, because we're talking about elastic potential energy, not gravitational potential energy. You'll see that the halves cancel out, and we're solving for x. And that's the formula you end up with. X, because it's x squared in the original, x equals the square root of mv squared over k. Plug the numbers in, again, fairly straightforward, and you get an answer of 0.194 meters, which is 19.4 centimeters. Okay, so here's what I was referring to with example number 15. Here's a similar example, which is a little more involved. So we've got a skateboarder, and obviously at this point here, they're already going downhill, so they already have some kinetic energy and they have potential energy. So they have a combination of both. And the question says, they gives you the mass of the skateboarder. Skateboarder passes point P, that is 3.9 meters above the ground, above the bottom of the hill, with a speed, so that's h, and the velocity is 1.25 meters per second. What is the skateboarder's kinetic energy as he passes another point Q, that is 1.15? So this is 1.15 meters, and the question is asking for the skateboarder's kinetic energy. So they could ask for kinetic energy, or they could ask for velocity. If they ask for velocity, it's just one extra step. But they're asking for kinetic energy, and so it's going to be an EM equals EM prime. In this case, we have both kinetic and potential energy before, and then afterwards, once the skateboarder gets to Q, well, they're still going to have both. So it's still going to be EK prime plus EP prime. Okay, and so what are we solving for here? We're solving for the kinetic energy at Q. So we can rearrange this formula if we want. EK prime equals EK plus EP minus EP prime. So we just took this one here and moved it over to the other side. And so it's going to get kind of messy. And therefore, the EK prime equals 1/2 mv squared. So that's going to be this velocity plus mgh. So that's going to be this height minus mgh prime, which is going to be that height. All right, plug your numbers in. Mass, initial velocity. Don't forget to square it. Mgh 3.9 minus 1.15. All right, so that's somewhat long and convoluted. Let's just plug that into the calculator because I didn't do this. 1.5 times 76.4 times 1.25 squared. I'm just going to put equals at that point, plus, and then I'm going to put this in brackets. 76.4 times 9.81. Reminder, no negatives because it's energy for gravity, times 3.9, end of brackets, equals, minus bracket 76.4 times 9.81 times 1.15, end of brackets, equals, looks like it turns out to be 2,120. Right there, A. So the answer for 17 is going to be A. Okay, we'll stop and then we'll do one more video for this review.